Hello everyone. So in the previous videos, you learned how to determine domain of vector function, right? So right now we will try to focus on techniques involved to sketch the parametric curve based on the given vector function. So in the beginning of Chapter 2, we have introduced the definition of vector function. Vector function will produce parametric curve. So, let's try to solve this example 2.1.1.3 on page 120 together. So right now, for the first question A, you have been given with this vector function r is equal to ti plus j. Right now, I would like you to pause this video and try to recall back what you have learned on chapter 1.4 about vector equation of a line. So if we can remember, vector equation of a line is given as vector r is equal to vector r naught plus t vector v. Am I right? So right now, try to imagine the question that has been given to us. Try to reposition the expression and then somehow try to make sure it will resemble the vector equation of a line. So when I try to rewrite my equation, I will get j plus ti. Am I right? So right now, as you can see from here, since it involves I and j component only, what should you know is that it will give you a parametric curve that lies in two-dimensional coordinate system. So it will only involve I and j component. So right now, I can also represent my vector function in this way, right? 0i plus j plus ti plus 0 times tj. And then I will have 0, 1 plus t, 1, 0. Am I right? I'm trying to write it and then I will make sure vector that is associated with t at one place and vector that has no connection with t at one place. So I will have this information. As you can see from here, vector 0, 1 is actually position vector prior to point P0. Meanwhile, vector 1, 0 is position vector of point P. If you try to relate with the lesson that you have obtained in chapter 1.4. So right now, since we are able to relate it with vector equation of a line, your parametric curve should look like a line. And we know that the component involved in this vector is only I and j component. So right now, if I try to illustrate the parametric curve, so I'm going to have this y versus x axis. And then, as you can see from this expression over here, it will give us knowledge that this straight line will be passing through a point 0, 1, and at the same time the parallel vector is vector 1, 0. So right now, try to locate where is point 0, 1. Point 0, 1 is somewhere over here. Let me change the color of my pen. So 0, 1 is somewhere over here. And then as you can see from here, there should be a line, and this line should be passing through a point 0, 1. And at the same time, you need to know how to sketch vector 1, 0. So vector 1, 0, there is some changes at x-axis. So right now you will have something like this. Okay, 1, 0. Changes occur at x-axis only, and nothing happen at y-axis, since your jth component of your vector parallel to the line is actually 0. Then you can conclude that this is the parametric curve, and it should has the same direction of the parallel vector. So that's how you sketch vector function which will give you a parametric curve. Okay, let us try question number 2. You have been given with this question, vector RT is equal to 1 minus t, 2 plus t. So right now, what should you do? Try to present your expression in the form that you are familiar with. So if I try to rewrite my vector function, I will get 1 minus ti plus 2 plus t j, and then I'm going to make sure I am able to separate vector that is associated with t and vector that has nothing to do with t. So I will get I plus 2j minus ti plus tj, and then I will get 1, 2 plus t negative 1 and 1. So in this case, somehow it looks similar to vector equation of a line, which is vector r is equal to r0 plus tv. And then based on the knowledge that you have gained in chapter 1.4, by right it will trigger something to your mind, and then you will end up having a line as the parametric curve. So in this case, the line will be passing through point 1, 2, and at the same time the line will be the vector on the line will be parallel to vector negative 1, 1. So what should I do right now? I'm going to sketch y versus x, and then I'm try to locate point 1, 2. 1, 2 maybe somewhere over here. 1, 2. Then I try to sketch vector parallel, which is negative 1, 1. So how to sketch a vector? It should start at the origin, so it will move 1 unit. So let me use dotted line instead of solid line. So it will move 1 unit to the left and 1 unit up. So this is vector negative 1, 1. So when you try to sketch the parametric curve, make sure your parametric curve somehow parallel to vector negative 1, 1. Therefore, the best way to illustrate this vector function is by having this kind of direction. Sorry. Yes. So that's how you sketch parametric curve based on the vector function given to you. I hope you know how to solve question C, because it will give you the similar parametric curve, but this time around it will give you a line in three-dimensional coordinate system. So let us focus on solving question D and E. For question D, you have been given with a parametric or a vector function in the form of trigonometric function. So in this case, you will get vector RT is equal to A cosine T and A sine T. So if you look closely, if you don't have any idea on how to solve this problem, why don't you try to present it in the form that you familiar. So in this case, I will get x is equal to A cosine T and y is equal to A sine T. So in this case, in order to get rid of the parameter T, I'm going to use trigonometric function, or not trigonometric function, I'm going to use trigonometric identities. So in this case, I will have x squared is equal to A squared cosine squared T and y squared is equal to A squared sine squared T. Then I will get x squared plus y squared is equal to A squared cos squared T plus sine squared T, which I will get A squared. By right, this equation will give me a circle with radius A. Therefore, based on our knowledge on chapter 1.1, if x is equal to some cosine function, you will end up having anti-clockwise direction. Now let's try to solve example E. Okay, you can use the same method when we solve example D. 2 cosine T, 3 sine T. So in this case, if you don't have any idea what kind of parametric curve you will end up with, so let's try to solve it one by one. X is equal to 2 cosine T and y is equal to 3 sine T. So right now I'm going to use the same procedures where I will apply trigonometric identities to get rid of the parameter T. I know that x over 2 is equal to cosine T and y over 3 is equal to sine T. So x squared over 4 is equal to cosine squared T and y over 3 squared is equal to sine squared T. I will get x squared over 4 plus y squared over 9 is equal to 1. So this is equation that will give you ellipse, where this ellipse will measure at y-axis since 3 is greater than 2. So I will sketch my ellipse. Again, since x is equal to some cosine function, you will end up having anti-clockwise direction. So that's how you solve this question. So for example 2.1.1.4, this equation or this vector function will give you a curve in three-dimensional coordinate system. So as you can see, based on the illustration given on your module, you will end up with a circle that is elevated 2 unit at z axis, since you have this vector function rt is equal to cosine t sine t and 2, and then x squared plus y squared is equal to 1, which will give you a circle in two-dimensional coordinate system. But this vector function will end up in three-dimensional coordinate system because there are all three component vectors such as I, j and kth component. So that's why you will end up with z versus y and versus x. So right now you will end up with a circle which has been elevated 2 unit at z is equal to 2, and then it will end up with this direction. Let's take a look at this example where it is quite different compared to what you have in the previous example, where this time around the range for t is given, such as for question 1, range for t is in between 0 and pi over 4. So instead of having the whole curve, you will sketch the curve according to the range given to you. So in this case, vector rt is equal to 2 cosine 2t and 3 sine 2t. So if you look closely at the coefficient for each function, since they are not sharing the same coefficient, you will end up with parametric curve that looks like an ellipse. So in this case, since x is equal to 2 cosine 2t and y is equal to 3 sine 2t, and range for t is in between 0 and pi over 4. So right now you have to solve the parametric equation based on the range of t given to you. So in this case, if t is equal to 0, x is equal to 2 cosine 0, y is equal to 3 sine 0, you will have 2, 0. So it will start at point 2, 0. So when t is equal to pi over 4, x is equal to 2 cosine pi over 2, and y is equal to 3 sine pi over 2. And if you use your calculator, by right you will have 0, 3, and then you will have this parametric curve. It should looks like a portion of an ellipse. So it starts at 2, 0, and then it ends at 0, 3. Then that is the orientation of your parametric curve. So I hope you are able to solve the next example where t is ranging from 0 and pi over 2. And then if you curious enough, maybe you can try and understand example 2.1.1.6 sometime. This equation or this question will be given in the assignment, because it will be very hard when you try to sketch the parametric curve manually. You need to use appropriate software to illustrate the parametric curve based on that vector function.